Okay, so we have these two equations, two functions essentially to graph. Leave this up here, make sure the camera stays focused. So. If a vertical stretch by factor 2. In horizontal shift and a vertical shift, the +5. So this is the basic sparring function with this vertical shift and these vertical stretch and these horizontal and vertical shift. So we start with a basic sparring function. We've got to vertically stretch it by a factor of 2, so we want to leave ourselves a reasonable amount of room. So I'm going to put 4 here on the y-axis. And then I'm going to put, then we got to go out to x equals 3. So I'm going to put 4 here on the x-axis. Oh, of course, we have -4 out here, -2, -1, so. Okay, my basic sparring function then would have a graph like there. With these points, and of course, you got the 1/2, 1/4 point way down here, and you sketch a curve. It's pretty bad, but it's not very symmetric. But now to vertically stretch it, you take each point, and I'm just going to use 5 points. Because I messed it up between here anyway. I move each of these points twice as far from the x-axis in the same direction. In other words, I double the y-coordinate because we vertically stretch by factor 3, the y-coordinates double. By factor 2, y-coordinates double. So this point is going to move up here. And this point is going to move up all the way to x equals 8 or y equals 8. And this will move up to where y equals 2, and this will move up to where y equals 8. And here we have the graph vertically stretched. So we have the y equals x squared graph. Here we have the y equals 2x squared graph here. And that's going to be the shape and the, that's going to be the shape. Okay. To the extent that I did that correctly. It's always a little lopsided. I never have been good at getting those things so they aren't lopsided, especially in the board where my head's locking what I'm looking at. No excuse, I'm not very good at that. Okay. So anyhow, we horizontally shifted 3 units. Can we replace x by x minus 3? That horizontally shifts at 3 units. So now we're over here. So the origin shifts here. And then these points shift accordingly. And we also get the points over here. I'm not going to draw all the arrows, but it's going to look like this. So this is y equals 2 times x minus 3 y squared. You can check that. Let x equal 4. Okay. Then x minus 3 is 1. And 2 times 1 is 2. And right here is y equals 2. That's point is 4, 2. Okay. We have the point 5, 8. X is 5. We have 2 squared, which is 4 times 2 gives us 8. So out here, that's all. X equals 5. Okay. Now what do? We shift everything 5 units up. So we've got the vertical stretch. I'll circle that in yellow. That goes with the yellow graph. Horizontal shift of +3. That goes with the blue graph. And then we'll do a purple graph. I haven't done a purple graph in a while. I'm saving it because it's so rewarding. Okay, so we shift every one of these points up 5 units. Well, this will go up 5 units. Okay, it gets up there. So there's 7, 6, 5. This point shifts up 5 units. And this point shifts up 5 units. So we get these 3 points, and we can do the same thing with these 2 points. But I'm not going to clutter up the graph. Just going to draw a nice one out. That one came out better than usual. Okay. So we've taken this function and we've added 5 to all the y coordinates. That gives us a vertical shift of 5. And now the equation is y equals 2 times x minus 3 squared plus 5. Now the y-intercept, it's always good to find the y-intercept. If we let x equal 0, we get then 3 squared, that's 9. Multiplied by 2, we got 18. Add 5, we get 23. So 23 is up about here. Makes sense that graph might intersect the y-axis up there somewhere. But you probably didn't leave yourself room in the graph, and I didn't. So there's the picture. The other thing is, of course, the axis of symmetry. X equals 3. And the vertex is 3, 5. Okay, now that equation, or that function was in vertex form. So we could immediately read off the vertex as 3, 5. But we really want to think through the transformations because we want to keep reinforcing that because we're going to be using it throughout the course. Didn't necessarily have to use transformations, except, if you have the vertex and the y-intercept, you could still draw a pretty reasonable approximation without even having any of these other points. Okay, and that would be acceptable for what I ask you to do. But I wanted to include all the details. Okay, so now we want to graph y equals x squared minus 8x plus 4 intercepts. Zero 4 should be pretty obvious. Now, again, I'm assuming part of your picture of the universe that you find the y-intercept by letting x equal 0, you find the x-intercept by letting y equal 0. You've done it a number of times with straight lines, you're doing it here. Okay, and you're going to continue to do it. It gets more complicated. But you're always going to ask yourself, what's the x-intercept? Well, that occurs when y equals 0. What's the y-intercept? That occurs when x equals 0. It's the first thing you usually do. There are other things you could do first, and usually that would be okay. But anyhow, we got 0, 4, and I'm going to just write it out. Eight plus or minus the square root of 48 over 2, 0. Because you can approximate this a little more accurately than you would if you divided the 2 in here and factor the 4 or the 16 out of the 48 and everything else. Now, if you have a calculator, you're going to get it anyway. On a test, I think I've got problems of this nature set up so that you get integers if you do the quadratic formula correctly. $7.5 is okay here. So those are reasonable approximations. And the axis of symmetry is that x equals 8/2, which is 4. Now, that's one way you can find it. You use the negative b/2a, comes out of your quadratic formula. Make sure you know where that is in the quadratic formula. Review what I showed you if necessary. So you can immediately get your axis of symmetry when you have the function in this form. Okay? It's negative b/2a. I would not memorize that as a separate formula because it's right there in the quadratic formula if you just throw out that plus or minus the square root. If you want to memorize 2 formulas, okay, but you don't really have to. Okay, axis of symmetry is there. X equals negative b/2a. Okay, so that's 16 minus 32, which is negative 16 plus negative 12. Everybody get negative 12? Make sure my arithmetic is correct because I'm not in my best form right now. Okay. Lots of stuff. Yeah, just losing a little bit of sleep. Except it can affect what I do here. Okay, so y is negative 12. So now we have what we need. Okay, we need a y-intercept at 4 and a vertex at negative 12. So our graph is going to want to at least go from negative 12 up through 4. So you cut that in half, you get negative 4. So should be a little lower than that. Getting zeros here, so this is where your x-axis is going to be. And you come out to x equals 4. Here's 2, here's 1, here's 3. I'm going to bring it out to 8 because the vertex should be at 4. Okay. So there's a scale that works. Here's the vertex. Or negative 12. Here's your y-intercept. 0.04. And at this point, you can sketch the graph. Okay. It'll be pretty steep here. Level off here, they'll come up like this. I fudged a little bit because I know what the zeros are. They're going to be at like -1/2, little more than -1/2, a little less than that. But this picture confirms that. Consistent. Okay. There's a 0 at approximately 7.50. And here's a 0. Approximately 1/2 0. You could have drawn the zeros before you drew the graph because it would have fit in with everything else. Would have worked just fine. So if you had this point, these 2 points, and this point, and then you drew a parabola vertex here, it'll work out just fine. Okay, well, that's what you need to know about how to graph parabolas. You should be able to graph them in vertex form without having to use a quadratic formula. Okay, one other thing over here. One other comment. If you want to find the zeros, they occur when y equals 0. So you solve the equation 2 times x minus 3 squared plus 5 equals 0. You get subtract 5 from both sides, you're going to get this equal to -5. Divide both sides by 2, you're going to get x minus 3 squared equals -5/2. How do you know there's no solution to that? The square can't be negative. And this is negative. So in formal mathematical language, we say, ain't no zeros. Okay. Just to emphasize the point, use a little vernacular English. Okay. No zeros. And that's consistent with the graph. See any zeros there? There's a 0 here, there's a 0 here. But when you lift this thing up off the axis, one more zeros. Okay. Okay. Now let's see what else you might run into. Okay. Here's the height of a rocket. Okay. My grandson's in a rocket team. He's an electrical engineer. And his task on this thing is figure out how to put the fins on it. Okay. It's a tube about this big around at this high. Goes up quite a ways. So they're dealing with a lot of this stuff. Now, why an electrical engineer gets tasked with the mechanical thing of how to put the thing on? Well, we went to horse race this weekend, and on the way back, we were brainstorming. He asked me, I'm thinking of doing it like this. How else could you do it? You know, we came up with some good ideas. Just give and take. It was kind of fun. So that might be his rocket. I hope his rocket goes further than that as well. But hope it at least gets off the ground. That would be big improvement to just blowing up on the ground, right? Okay. So here's a rocket. Here's the function height versus time. And I'm pretty sure that it gave you height versus time, because that's would be a height versus time function. Okay. What do you do with this? Do you read the problem and try to figure out what it's asking you? No, you have a quadratic function here, you graph the thing. Then you have a graph to look at while you try to figure out what the world the problem's asking for, right? Okay, so we graph it. Well, I'm not going to go through the detail of graphing it, except to say, well, obviously the t-intercept in this case instead of x-intercept is negative b over 2a, right? It's negative 200 over 10, that's 20. Okay, this thing's going to go at least 20 seconds before it hits a vertex in its path, which is its highest point. So the big thing I need is I need to then say, well, immediately my axis of symmetry. Is that x equals 20? So right here is 20 on the x-axis. What other things do we know? Well, now that we know the axis of symmetry, it's going to probably be a good idea to find the vertex. Because then you know how to scale your y-axis. Okay, so the vertex is that y equals negative 5 times 20 squared. 20 degrees, 20 squared. Plus 200 times 20 plus 100, okay? Well, 20 squared is 400, 5 times 400 is 2,000, and it's negative 2,000. This is 4,100, so it's at 2,100. You check my arithmetic. I'm relatively confident. So we got 2,100. There's a vertex. Y-intercept y equals h of 0. You plug in 0, the t terms go away, and the t squared term we have 100. So here's 2,100. So you know, here's 1,000. Here's 2,000. Down here's 1,000. This would be maybe 500. This is a little high. 400, 300, 200, 400. So here's the y-intercept. This should all be reflexed. You automatically do this. Anytime you see a quadratic function, you just do it. Doesn't take long. It's not hard. Yeah, if you got to do the numbers without a calculator, it can be hard. In this case, it isn't. So now we pretty much know what this thing's going to look like. It's going to come up here. It's going to peak here. It's going to come back down. Why is it upside down? Because you got a negative here. If you start with your t squared function or your x squared function, and you do negative 5 t squared, that's going to flip your basic squaring function upside down and stretch it by a factor of 5. So you imagine your basic squaring function, which is going to be hard to draw on this graph. Just imagine it. Turn upside down, stretch by a factor of 5, and then move so the vertex goes from here to here, and that's the graph we're going to have. And well, let's find the intercepts, because the intercepts are often important. Okay. The intercept. Yeah. Print kind of small, but you know what numbers go in here. You're careful. This is negative minus 4 AC. Minus 4 times negative 5 times 100. Okay. Well, 4 times 5 is 20, and negative times negative is positive. So that's going to give you 2,000. 5 squared is 25. So it's going to be 5. Plus or minus the square root of 2025 over negative 10. They're being nice to you. I'm being nice to you. And I'm pretty sure that's the square of 45. I didn't know that when I put these numbers in here. Of course, your book had a negative 4.9. So your discriminant's going to come out some decimal. Okay, well, you work that out. Negative 5 minus 45 is negative 50. That would give negative 50 over negative 10 is negative 5. And then 40 negative, no wait, that's negative 50 over negative 10. Well, that's not working out at all. So give me a 0 and t equals 4. And really the problem is this isn't negative 5. I was looking at that negative 5. So you got to keep an eye on it. That should have been a negative. That should have been 200. So be careful like I'm not, but that's negative 200. You see, I was getting ridiculous results. I was getting negative 4 for one of the intercepts, which is plausible. This thing's going to come down through here and just somewhere in the negative y-axis is going to hit 0. But I was also getting 5, which is here, and I know that a parabola with vertex here and a point here is not going to go through 0 here. I pretended to make that mistake just to show you how to use common sense sometimes. Okay. So negative 200 minus 45 is negative 245. Still something wrong with this. I'm gonna turn the camera off while somebody here tells me what bonehead thing I just did. Apparently, first thing to go is clerical ability. Okay, just put the wrong numbers in the wrong place. Okay, probably should have written the thing out and done it very methodically. So take a lesson. And don't do like I do. That's 40,000. Okay, and that's 2,000. So now we don't get a nice even number. We get 42,000. I'll watch me screw this up too. Square root of 420 is about 20 and a half. Reasonably close, 20 and a half. That would be again something seriously wrong with that. I'm going to give you the right one intercept. Man. Oh, good. I didn't record that. Okay, again, my clerical ability apparently is the first thing to go. But 200 should have gone here, not 5. Got that in my head. Wrote it down without thinking. Okay. It didn't work out. It was not going to fit this graph in any way. My zeros are not here and here. If I draw a parabola through here, got a 0 out here, a little past 40, and one here, a little past 0. Okay. Well, if I put 200 here, I get this. And the square root of 42,000 is pretty close to 205. So I can do that. One of a few things I'm able to do today, apparently. If you add those up, you either get -5 or you get 405 over 10 at 40.5. Okay. Now that makes sense. Clearly, when you draw this half of the parabola have a 0 over here. This half will have a 0 over here, equally distant. So 40 would be about here. And now my zeros are at -5. And 40.5. Okay, now you can read the question. The question asks, how high does the rocket go? And when does it splash down? Okay, this is an applied problem. One of the first things you should have done is say y equals height. If you know that the height is in meters, I don't know if the question asked told you that, but it would be in meters, and you'd say height in meters. So when you look at the graph, you don't have to think, okay, what's that mean again? You got it right there. And this is time. Could go more details on time since launch, but time is probably sufficient in this context. Okay, so how high does it go? Well, here's your height. You got points in the graph that go all the way up to 2,100, meaning 2,100 meters. Okay, which is over a mile. That's not too bad. It's about what that rocket team is probably going to get on their test flights. Now, when they go out to the desert, Nevada, or wherever they launch from, they're hoping to get 20 miles. 100,000 feet, basically. And they got to launch out there because that will interfere with aircraft. They got a test site up at Virginia Tech where they can launch low launch up to 1,000 feet or something like that. Okay, so they couldn't even do this launch there because again, aircraft could be at that height. Okay, and where does it splash down? Now, the ocean's not that close to Virginia Tech. So they got a big lake. Well, they're not trying to splash down. It comes down with parachutes. They can recycle. Keep recycling until it blows up, right? That's what you do with rockets. It's just great that they're able to recycle, the big launches. I don't think they're going to recycle the Artemis. That's too good. Okay, so, or they pronounce it Artemis. I don't know. I never listened to them. I just try to mislead them. Okay, all of them. both sides of the aisle. Okay, so anyhow, over here. When does this blast down? Well, 40.5 seconds. So it's up there for the better part of a minute, goes up about 2,000 feet, pretty good launch. Not gonna do that with a backyard hobby kit. Okay, as soon as you have the graph, do you understand what I'm saying? Is you read the rest of the problem and the answer's right there, almost jumping out at you. So you automatically graph any quadratic function you have a question about. Doesn't have to tell you, graph this, you know you got to graph it. Okay. Now, maybe you know it well enough that you can do it by solving an equation without the graph. But for right now, you better be graphing. Here we have a function. Can't read it from the back or something. X minus 3, x plus 5, x. That's a polynomial because you know if you multiply these out, you're going to get an x cubed term, an x squared term, an x term, and a number. And the number on the end is going to be 3 times 5, negative 15. Okay. And the x is just going to be x squared because there's no numbers in front of x. So that equals x squared plus, sorry, x cubed plus x squared plus question mark times x minus 15. Just so you know, there's some number here, some number here. You multiply it out and just a couple, less than a minute, and you can figure out what those numbers are. In fact, you probably figure them out right now. You know, this is going to be 2, and this is going to be, make me think. No. Actually, the negative 15 goes here. Because I don't remember that. I did something wrong. Okay, this isn't important. I just wrote it down to show you if you multiply it out, you can do that. But you don't. This is what you want to look at in order to graph it. So what are the zeros? What's the y-intercept? And what's the long run behavior? You ought to be able to answer that in a minute. I'm going to give you a minute to think about it. Okay, I didn't give you enough time to think through that. I mean, if you're on top of it, when you come into the test, you want to be able to do that in your head quickly for a function that simple. Okay, that's what you haven't done it before. What do you ask? How do you find the zeros? That's when y equals 0, right? Can you give me a number here that makes y 0? Just pull up fingers. 3. X is 3, y is 0. Give me another number, gives it 0. Negative 5, right? There's one more. What would that other one be? 0. Okay. When x is 0, the whole thing is 0. That's obvious. You just set this equal to 0, set this equal to 0, and set this equal to 0, and you got it. If I have, 47x minus 398, well, you grab 400, whatever x minus 398 equals 0. Solve it. Just a linear equation for you to solve. Okay. Y-intercept. What's y-intercept? Yeah. Y-intercept occurs when x equals 0. When x equals 0, the fact that you're multiplying by x makes the whole thing. But I'll write it out. 0 minus 3 times 0 plus 5 times 0. As you plug in x equals 0, just to remind you to plug in x equals 0. That should be second nature to you again. When you get the zeros in the y-intercept, you need to know exactly what to do. And if you know exactly what to do, it's really easy. Really easy. Okay. And then the long run. So x goes infinity, y goes to infinity. As x goes to infinity, y goes to negative infinity. Okay. So now you got your graph. Just put your zeros down here, -5, 0, 3. Your y-intercept is at 0, and that's also a 0 of the function. It's up here. Sorry, it's down here. Up here. So it comes up from here, turns around, comes back down, goes back up. And there you got a graph. Okay. Now, by contrast, we've got over a minute. Okay. Here's another function. Now, same zeros because I've got exactly the same package here. Now the y-intercept is a y equals 45 because you're squaring the 3. So you have 0 minus 3 squared, which gives you 9 times 5, give you 45. Okay, just plug it in. I don't have to tell you how you calculate that. It's easy to calculate. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y still goes to infinity because you have a fourth power. If x is any negative number, big negative number, but you're squaring a negative number, which makes it positive, then multiplying by a negative, which gives you a negative, and multiplying by a negative, which makes it positive again. It's going to be humongous and all that stuff. So now we can draw the graph. Well, I should put that exercise on. Now we can draw the graph. Same zeros. But it's up here and it's up here. And the y-intercept is positive. So the y-intercept is not 45, it's still 0. Keep an eye on me. I know what I'm going to say next. Okay. So how are we going to get through this point, this point, this point, coming up from here and out from here? We can't go through the x-axis anywhere but at the zeros. Because any other number except -3, -5, or 0 is going to give us something that isn't 0. Okay. Y is not going to be 0 unless we're at one of those points. Well, means we come down from here. And we do this. Why? Because x minus 3 is squared, and x minus 3 squared would be a parabola. So it acts like a parabola here. Okay. And I'll say x minus 3 squared is locally parabola. Now, what the book is going to tell you is, or the open math is going to tell you, is that this thing has degree 2. So this is a 0 of degree 2. These zeros, if you look really close at this point and this point, the graph looks like a straight line because it doesn't have much room in a small window to change its direction, change its slope. Okay. So these zeros are degree 1. So there you have it. If you know that much, the rest of it is pretty easy. If you had a 0 of degree 3, it would act like a cube function. It would flatten out, but then it'd go on through the axis.